Hi. In this session, we will be discussing about rooted trees. Okay, so what are rooted trees? Rooted trees are basically trees in which one vertex is special or that is distinct from all other vertices. Okay, so it has a special place or special importance in that tree. So such trees in which a particular vertex is distinguished from all other vertices is called a rooted tree. Okay, for example, if you can see this diagrams here, so you can see that this vertices. So this vertex in this diagram is marked as important, so that's a rooted tree. And again, this vertex here is very important, that's called a rooted tree. We have marked a special, we have made a special marking there. And so you can see that all these vertices have been marked distinctly in that graph, so they are rooted trees. And similarly, this vertex here is marked distinctly, so it's a rooted tree. Okay, so basically these vertices are special. So when you model real life problems, they may be distribution centers, or there may be where the company's headquarters may be lying, or they may be some very important person in the hierarchy. Okay, so when you model real life situations, you basically use rooted trees to model situations in which a particular person or a particular area or a particular office is important. Okay, so in order to show that, we will be using these rooted trees, and this uh, basically this important vertex is always called a root. Okay, we also call that vertex as a root. Okay, so the most important vertex there. Okay, so such trees are called root trees. Okay, and basically this is very useful in computer science for making working with tree based data structures. We'll see about it in later. Okay, and in some other textbooks you can always find many related terms with related to this roots there. So let us see that. So basically in some textbooks and some literature, there are terms called branch. Okay, branch means basically it's an edge. It's another name for an edge is called branch. Okay, so basically in a rooted tree, the edge is sometimes called as branch, and depth of a vertex is basically the distance of any vertex from the root. For example, the depth of this vertex is basically 1, and depth of this vertex is basically 2. Okay, and in this tree, if you look at this vertex, the depth of that vertex is actually 2 there. Okay, so distance from distance of any depth of a vertex is basically distance of any vertex from the root. Okay, and similarly there is another concept called level of a vertex. In many textbooks they have defined it differently. In some textbooks what they define is basically it is the number of vertices between the root and the number of vertices between the root and the concerned vertex. So that is called level of a vertex in according to some textbooks. Okay, in our textbook what we are doing, however we are going to define level is basically it's just the just again it is same as it is again defined as same as depth. Okay, so basically level here also means the distance from the root. Okay, so in our textbook level of a vertex is being defined as basically the distance from the root. Okay, so we will be using that definitions, but if you look at some other textbooks or if you look at internet, level is basically the number of vertices between the root and the concerned vertex. So usually the level of root is defined as 1, the next vertex. So basically in most textbooks the level of root is defined as 1, the next vertex will be defined as 2, the next vertex will be defined as 3, etc. But in our textbook it is defined, level is basically defined as again the distance from the root. So the root will be at level 0, and the first vertex will be level 1, the second vertex would be at level 2, the third vertex would be at level 3. So we will be using this convention. Okay, so in this, if you look at this tree, the level of this vertex is 0, the level of this vertex is 1, this vertex is 2, again this vertex is 2. So basically it's the distance from the root. Okay, so I hope it is clear what do we mean by level of a vertex and also depth of a vertex. So both are used interchangeably in our textbook. Okay, so when you refer some other textbook, you should be clear of the notation, you should be using the notation which is given in that book. Okay, so for our purpose we will be using this definition there. Okay, again we will study what do you mean by parent. Okay, so this also is some common term there. So if you look at this graph here, okay, we will say that this vertex is actually the parent of this vertex. So basically this vertex is said to be the parent of this vertex, and this vertex is said to be, second vertex is said to be the child of that vertex. Okay, very simple thing. Okay, for example, this is the parent of this vertex and he is the child of this vertex. He or she is the child of that vertex. Again, this is the parent of these two vertices and their childs are these two vertices. Okay, so I hope it is clear what do you mean parent of a vertex, child of a vertex. Again, leaf is a vertex. Basically leaf is a vertex is basically an n vertex. Okay, so leaf is basically an n vertex. You can see that. So in this graph there are many leaves are there. This is a leaf, this is a leaf, this is the base. So they are all n vertices, so they are called leaves there. Okay, and height is the maximum level of the graph, maximum level possible in that graph. Height is basically the maximum level possible in that graph. Okay, So height is basically the maximum. So what will be the height in these cases? Okay, if you use the textbook notation, the height of this tree is basically this level is 0, this level is 1, this level is 2, this level is 0, the height is 3 there. And if you look at this graph, this level is 0, this level is 1, this level is 1, this level is 2, so the height is 2 there. Okay, so if you look at this graph, this level is 0, this level is 1, this level is 2, this level is 3, so here the height would be 3. So I hope it is clear. So basically we tried on definitions from other sources. So we need only two main things from this section, that is basically what do we mean by level and what do we mean by height. Okay, so level is basically the distance from the root and height is the maximum level possible. So that's the only thing which we need to know now. Okay, so other definitions you can look by yourself. Now we will study a particular class of rooted trees called binary trees. Okay, so we will study a particular class of rooted trees called binary trees, and the definition of binary trees is basically defined as a tree having exactly one vertex of degree 2, a tree having exactly one vertex of degree 2, and each of the remaining vertex have degree 1 or 3. Okay, for example, if you look at this one, this vertex has degree 2 there, and this vertex has degree 3, this has 1, this has 1, this has 3, 1, 1. So there is exactly one and only one vertex with degree 2, and every other vertex has degree 1 or 3. Okay, so such a graph is called a binary tree. So basically this vertex which has degree 2 is distinguished from all other vertices, so this will act at the root of that binary tree. So the vertex having degree 2 will be the root of that binary tree. Okay, so also please mind that this definition is not same as in other textbooks. In other textbooks they define binary tree as a tree in which every vertex has at most 2 children or something like that. So that is not required because that is an altogether different definition, but some properties are common, but you have to be careful. In our textbook we define binary tree as a tree having exactly one vertex of degree 2 and every other vertex having degree 3 or 1. Okay, it is not the same definition in other books. Even if you look at Wikipedia also, the definition would be different, but for our sake we will be following only the textbook definition. Okay, so binary trees can be used for other trees also. For our case, a binary tree will be a tree in which there is exactly one vertex of degree 2 and all the vertex have degree 3 or 1. Okay, so basically these trees are very much useful in searching algorithms. We will see that later now. Okay, so each of the levels, so we can see this. We have drawn two binary trees here. So each of the levels actually denotes some test. Okay, and with having two outcomes, and if you have an outcome here, so if the outcome is this, that means the text has finished, the procedure has finished there, or else it will go to the next level, it will conduct a test, it will have again two outcomes. If the outcome is this, again it will go to this level, and there again a test will be conducted, and if the outcome is this, the test will be terminated there, or else it will go. So basically these type of binary trees are used to model search algorithms. Okay, so binary search algorithms and everything, so we'll see to that later. So I hope this is clear what do we mean by binary tree. Okay, now let us see some common properties of binary tree. The first property is very simple thing: the number of vertices in a binary tree is always odd. The number of vertices in a binary tree is always odd. So what the property of binary tree is that there is exactly one vertex of degree 2 and all the vertices are of degree 1 or 3. Okay, so if there are n vertices, you can see that there is only one vertex of even degree and n minus 1 vertices are of odd degree. Okay, because there is exactly one vertex of odd degree 2 and all other vertices have a degree either 1 or 3. So if there are n vertices, there will exactly one vertex has even degree and all other n minus 1 vertices have odd degree. And you know that in a graph, whatever graph it may be, the number of odd vertices is always even. That means this n minus 1 is even, which gives that n is actually odd. Okay, so when n minus 1 is even, your n is odd. So always the number of vertices in a binary tree is always odd. Very simple property. Okay, now let us try to find the number of pendant vertices in a binary tree with n vertices. Okay, so you know that in a binary tree there is one vertex of degree 2 and if suppose there are n vertices, and there are some vertices with degree 1 and some vertices with degree 3. So we are interested in those vertices with degree 1. Okay, so now let the number of pendant vertices or n vertices or vertices with degree 1 be actually p. Okay, so let the number of pendant vertices be p. Totally there are n vertices are there. Now can you tell me how many vertices of degree 3 would be there? Out of the total n vertices, p vertices have degree 1 and one vertex has degree 2. So these many vertices of degree 3 would be there. Okay, is it clear? Okay, now let us find the total degree of the vertices of the graph. So the total degree of the vertices of the graph would be, so basically there is one vertex of degree 2 plus there are p vertices of degree 1, so their total degree will be simply p, plus there are n minus p minus 1 vertices of degree 3, so their total degree would be 3 into n minus p minus 1. And what will be the value of this? Since this is a 3 and since there are n vertices, the total value would be simply 2 into n minus 1. So when you just solve this question or so solve this relation, what you can do is just 2 plus p plus maybe 3n minus 3p minus 3 is equal to 2n minus 2. Okay, so when you again solve it, you will be getting so what will you get? So it is 3n minus 2, so it is actually 2p. Okay, so minus 2p plus 3n. Okay, and again minus 1 is equal to 2n minus 2. Therefore your 2p will be equal to again 3n minus 2n, again that is 1, and minus 1 plus 2, so it is n1. So your p would be equal to n plus 1 by 2. So there are totally n plus 1 by 2 pendant vertices there. So very simple thing, you are just adding up all the degrees. Answer should be equal to 2 raised to 2 into n minus 1, and when you solve it, therefore p, you will get the answer of p as n plus 1 by 2. Okay, so out of n vertices, you have n plus 1 by 2 vertices of degree 1 and 1 vertex of degree 2. And how many? So basically, how many vertices of degree 3 would be there? You can say simply it will be n minus n plus 1 by 2 minus 1. Okay, and one other thing you can say is that in a root, okay, so apart there are actually, so those vertices in a rooted tree which are not n vertices or pendant vertices are called internal vertices. Okay, why is it so? Because they are not n vertices. So those vertices which are not having degree 1 are called internal vertices. Basically this is an internal vertex, this is an internal vertex, this is not an internal vertex. So how many internal vertices would be there? Okay, how many internal vertices would be there? Totally there are n vertices there. Out of that, the n vertices is basically n plus 1 by 2. So these many internal vertices would be there. That is actually 2n minus n plus 1 by 2. I think it is actually n minus 1 by 2. So there will be n minus 1 by 2 internal vertices. Okay, and you can also find the number of vertices with degree 3. Okay, so you can also see that the number of internal vertices is 1 less than the number of pendant vertices. Okay, why? Because n plus 1 by 2 minus 1 is actually n minus 1 by 2. So I can also deduce that the number of internal vertices is actually 1 less than the number of pendant vertices. Okay, that is also clear from there. Okay, so we have discussed all these things here. Okay, now let us move forward now. So basically, when you study about binary trees, the most common use of binary trees is in search procedures, as I have already mentioned. Okay, where each vertex represents a test with 2 possible outcomes starting from the root. Okay, so reaching a pendant vertex, I have already discussed that it will terminate the search. Okay, so so basically, when you design such applications or design such algorithms, what you require is that you need the test to terminate at a minimum time. Okay, so you need the test to terminate at a minimum time. So basically, in order to reduce the time of execution of that test, you need to design a program or algorithm in such a way that it terminates at a minimum possible time. So basically, we will be looking at by rooted trees which has minimum maximum level. Okay, so the maximum level possible or maximum level possible is actually the height. Thus, so we will be looking at designing rooted trees which has minimum height. Okay, so we'll look at both those things. We'll try to design rooted trees. We'll try to find a bound for rooted trees with n vertices which has minimum height and also maximum height. The minimum height problems are basically applicable for designing search algorithms which should be executed in minimum possible time. Okay, so basically when you have a binary tree, we know what it is and what level is there. What do you mean by level in a binary tree? You know what is the height of a binary tree. Height is basically the maximum level attainable there, and we will be interested in those binary trees which has minimum height. Okay, or we will also be interested in those binary trees having maximum height. So both of these extremes we will be looking into. Okay, so let us now look at, so suppose we have a binary tree with n vertices, minimum height in n vertices. Okay, so what will I do? I'll try to distribute all these n vertices at to the maximum at all levels. So at the first level or 0th level, I'll substitute one vertex. Okay, at the second level, I will have I can distribute 2 vertices So 2 vertices would be distributed at second level again at the like second level means the first level again. Okay, so in the next level, so basically now we are at level 1. So in the level 2 again, if I can distribute again 2 more vertices here. So in total I will have how many vertices at level 2? So I will have 2 square vertices again. Now over each of these 2 square vertices could again be supplied 2 more vertices. So we'll have 2 into 2 square more vertices, that is we'll have 2 cube vertices. For example, this vertex there will be 2 will be there, this vertex 2 will be there. So in total you have 1 2 3 4 again 5 6 7 8. So total you have 2 into 2 square, so 2 cube vertices again. Now each of these 2 cube vertices could be given 2 into again 2 again 2 children. So basically we have 2 into 2 cube vertices. So like that you can distribute it. So basically you can actually go on distributing like that. And suppose the maximum number of vertices that's possible in a k level binary tree is how? So if there are k levels, the maximum number of vertices possible is in the first level. 0th level there will be 2 raised to 0, in the first level there will be 2 raised to 1, in the second level there will be 2 square. So in the kth level it will be 2 raised to k. Okay, now you know that this is a geometric series, and you know the sum of a geometric series is basically what is it? It is equal to a into r raised to n plus 1 minus 1 by r minus 1. So here a is actually 1, r is actually 2 there. So we'll have 2 raised to k plus 1 minus 1 by 1. So that is simply 2 raised to k plus 1 minus 1. Okay, so that is the sum there. Okay, so that is the maximum number of vertices possible in a k level binary tree. Okay, now suppose you are being given you have been asked to construct a binary tree with n vertices, okay, having maybe minimum height. Okay, you have to construct a binary tree having minimum height. So what will you do is that you will try to distribute as many vertices as possible at each level. So the first level you can give 0th level you can give 1 vertex. At the first level you can give 2 raised to 1 vertex. Okay, and the second level you can give 2 square vertex. Suppose they are all till 2 raised to k, we need to find this k here. Okay, we need to find that kth level there. Okay, so for that, you know that the sum of all these are actually equal to 2 raised to k plus 1 minus 1. I need to find the value of that k there. Okay, so that is, so your n is actually equal to, suppose it is actually equal to this. So it may be not perfect because it can be 2 raised to k. So maybe you may need some more numbers here. Okay, suppose it cannot be perfectly, it cannot be written. For example, if your n is equal to maybe for example, if your n is equal to 11, so it cannot be written as 2 raised, can be written as 2 raised to 0 plus 2 raised to 1. So you will have again 2 square, so that is 1 plus 2 plus 4. So at 1 plus 2 plus 4 3 7, again 2 cube when you write you will be getting more than that. So when you have n is equal to 11, you cannot write it like that, but still you can write it like 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus some small quantity, so that your sum is actually equal to 11. Okay, so for time being assume that you can write n like that. For time being assume that your n could be written like that. So suppose you can n could be written as 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus etc plus 2 raised to k. Okay, it is not necessary, maybe you need some more values there so that you will be getting a sum as n. Okay, so for the time being just ignore that value. Okay, and suppose if we can write it like that, or I like 2 raised to k, what is the sum of the series? The sum of this series is actually 2 raised to k plus 1 minus 1. Okay, so let us try to find the value of k in terms of this n. So you have n plus 1 is equal to your 2 raised to k plus 1. So if you take log on both sides, so it will be log of n plus 1 will be equal to k plus 1 log 2. Okay, or your k plus 1 is equal to log of n plus 1 by log 2, or you can write this as simply log of n plus 1 to the base 2. So this is a simple result from logarithms. You know, log a by log b is log a to the base b. So your value of k is actually log n plus 1 to the base 2 minus 1. Okay, so that is the maximum level possible. So your k will be equal to log of n plus 1 to the minus 1. So that's the maximum level possible. Okay, sometimes you may substitute this k, you may get the value of k is equal to 3.5. So what is the maximum level possible then? That will be actually, so you will have 2 raised to 0 plus 2 raised to 1 plus 2 square plus 2 cube still you need some more values. That is why you got the values k is equal to 3.5. So the maximum value possible, maximum level possible is 2 raised to 4. Okay, so not the maximum level possible, the minimum level possible is actually 2 raised to 4, because after 2 cube also you have something left over. For that you need an extra level also. So the minimum level possible here is actually 4. Okay, so you will write that the minimum level possible for an n vertex graph, n vertex binary tree, is actually log n plus 1 to minus 1. This is the smallest integer function. Okay, so basically the smallest integers are greater than or equal to that value. For example, the smallest integer function of 3.5 is actually 4. Okay, this is the value of that. Okay, so this occurs, so this 3.5 type of things occurs when your n cannot be written perfectly like this. There may be some, for example, in our above example, above example with regarding 11, 11 could not be written as 11 is equal to 2 raised to 0 plus 2 raised to 1 plus 2 square, but you need some more values there. For in that case, when you try to distribute these 11 vertices, you can't include all these 11 vertices in these many levels, so you need an extra level there. So that is where the factor of 2 cube will come there. Okay, so that is where the factor of this smallest integer function of log n plus 1 to the base 2 minus 1 comes there. Okay, so that is the minimum level, minimum height possible in a graph binary tree with n vertices. Okay, so we have decided a lower bound there. Okay, now what is the maximum height possible? Can you just think of the maximum height possible? So the maximum height possible is will be trying to distribute as little vertices as possible. So when you start from your root, okay, so you can give a vertex here. Okay, so it should have a degree 2. So basically the 2 vertices should be supplied like this. So you can end it here, don't supply it again here. Second, you can distribute here again. So you will have 2 vertices there. Okay, so you will have 2 vertices there because there is only one vertex of degree 2 there. So you need to have 2 vertices there in that level. So you can stop it there again. Here again you can distribute 2 only. So it will go on like this. Okay, so when you have n vertices, you will be substituting or distributing the smallest possible number of vertices there. So when you start with the root, suppose your n vertices are there, you start with the root there. Okay, the root has degree 2, so 2 vertices will be coming out of that. Okay, you can stop this vertex you can stop the vertex here, and you can continue with this vertex and the next level. So this is the level 0, this is the level 1. So in the next level again, you need to supply 2 vertices because the degree of all the vertex is either 1 or 3 except 2. So this vertex should have degree 3. So okay, so otherwise it will have a degree 2 there, so it should be degree 3 there. So again you can stop at this level, you can continue this level again. You cannot give only a single vertex, because if you give only a single vertex, the degree of this vertex would become 2. That is not possible because in a binary tree only one vertex has degree 2. So again you will have to supply again 2 there again here. Again you can move on like this. Okay, so if you understood this pattern, can you tell me the maximum height possible there? Okay, so at the first level 1 vertex, at the second level 2 vertex, at the second level 2 vertex, etc. So at each level you are supplying 2 vertices. So at the first level only you are supplying only 1 vertex. So total, if there are total n vertices, one level 1 vertex is supplied to the root, so the 0th level, and all of the vertices are being distributed as 2 at each of the levels. So how many levels could be there? The number of levels is actually n minus 1 by 2. So this n, and you already know that n is odd, so n minus 1 would be even. So there will be n minus 1 by 2 levels again. Okay, so the first level, the 0th level, you are giving only 1 vertex. At all other levels you are giving exactly 2 vertices. So you are actually dividing this n minus 1 vertices into 2 pairs. So the total, the maximum level possible is actually n minus 1 by 2. Okay, so that is an upper bound there. So we have discussed that also. Okay, so I hope it is clear how you get the maximum level and minimal. And here also I have given an example of of distributing actually 12 vertices. We have actually distributed 12 vertices in the minimum level possible and the maximum level possible. Okay, so in the minimum level possible, first I supplied one there, one vertex there, and then we supplied 2 vertices on the next level, then we supplied 4 vertices on the next level, and so on and so forth. And the minimum we have distributed in such a way that there are only minimum number of vertices at each level. So this is the way of distributing the minimum number. Okay, so we can see that the maximum level here is actually 3, minimum level here is actually 3, and the maximum level here is actually 5, which conforms to the formula which we have already discovered. Okay, so that's clear here. Okay. Okay, so both of them are drawn when the cases n is equal to 11. Okay, and moving forward, a simple more concept is there. What do you mean by path length of a tree? This is also just really of academic interest. So what do you mean path length of tree is basically the sum of the levels of all the pendant vertices. For example, if you look at this tree, what's the path length here? So you look at the pendant vertices and their levels. So this vertex has level 1 and this n vertex has level 2, this has level 2, this is level 4, this is level 4. So sorry, okay, I have made a mistake here. So this vertex has level 3. Okay, so this vertex has level 3 because it's at the third level there. Okay, so this vertex has level 3 there, this has degree 3, and so level 3. Again, this vertices have level 4, and this vertex has level 4. So you are just taking up the levels of all the pendant vertices and then you are adding them up. Okay, so you take down the levels of all the pendant vertices and add them up. That will give you the path length of a tree. Okay, so that's the path length of a binary tree, and it is actually directly proportional to the execution time of an algorithm. Okay, so this gives an idea of the execution time of an algorithm. Okay, so because the pendant vertices are where your algorithm terminates. So basically the time taken to reach the pendant vertices is actually the time taken to execute that program there. So basically it gives you an idea of the execution time of an algorithm. Okay, so that is the final idea. So that's all. Thank you.